Oh, I hope people hear me. I hope people hear me. Let's see, I have to put this on the screen. Yeah, it's on the screen. I hope people hear me also at home. I'll be glad to have Avni from Northwestern, whose official title is something like width in arithmetic groups, and non-official is my other width problem. Nir, please.
Hey, thank you very much. Thanks for coming, everyone. This talk is more of a commercial break between the last two talks and the next two talks. So Alex talked last time about last two times about the congruent subgroup property and bounded generation, and I want to talk about so bounded generation is a wonderful notion, but there are some cases where it does not hold, and I want to suggest another notion of width, which is analog, but maybe wider, that might do the same thing as bounded generation, but will work in cases that bounded generation is known to fail. Okay, and everything I'm talking now is a joint work with Chen Meiri, who will talk next time again about, who will give the serious talk about width. So width is the following notion. If you have a generating set of a group, the width of this set is the diameter of the Cayley graph. Okay, so maybe I'll say differently. You know that every element in G can be written as a product of elements in X. To say that the width is less than 100 means that every element in the group can be written as a product of at most 100 elements of X or X inverse. Okay, now I want to use this notion for subsets that are not generating, and in that case, I will just I'll say that the width is the width of not of the whole of the Cayley graph, not of the whole group, but the group generated by X. Okay, so if I have any chance of writing an element as a product of some number of elements of X, I want to be able to write it as a product of at most 100 elements of X. Okay, so the first thing I want to say is that bounded generation is a claim about width. Okay, so let's talk about SLD, and I need to have high rank, so D is bigger than 2. So to say that, so bounded generation means that every element can be written as a product of a bounded number of elementary matrices. Okay, and the claim is that it's a width claim. It says that the width of the set of elementary matrices inside SLDZ is finite. Okay, now from bounded generation you can get different width claims. So I claim that if I take the conjugacy class of the unipotent element that whose single off diagonal entry is 1 at place 1, 2, then the conjugacy class of this element has finite width. Okay, and that's an easy computation. Let me just tell it to you. If you take this element, so let's, all the EIJ are conjugates. So I can take E13 and let me conjugate it by such a matrix. Okay, so my exponent is a notation from conjugation. Then it's easy to see that what you get is this matrix. Okay, so so this conjugacy class contains such an element, but it also contains, by the same reason, this element. Okay, this also belongs, these two belong to this conjugacy class. Okay, and therefore the ratio, maybe I'll put 1 minus x here, the product, okay, the product which is E23, so not 1, A minus x. The product which is this matrix belongs to E12 gamma times E12 gamma. Okay, and therefore every elementary matrix is a product of two conjugates of E12. And if the width of the set of elementary matrices is finite, then so is the width of this conjugacy class. Okay, now one of the proofs of bounded generation. Okay, there are several. I'm talking about the proof that I saw at.
Neil, can you go back to the previous slide for a second?
Yes.
What did you say that the first matrix I understand is conjugate to the E12?
By the same reason, the second matrix is also.
What's the second? It's
this one.
It's
Oh,
not.
okay.
It's written there.
Yeah, sure. It's the same matrix when I replace x by A minus x.
The arbitrary.
Another number. Okay.
But then how do you?
Sorry.
I don't understand why do you need if you want to prove that this elementary matrix is in the conjugacy class, why do you
I want to prove that the entire, yeah, it's.
If you take x can be any number, you could put right away.
But I want elementary matrix. There is one here.
Oh, I'm sorry. I see. You wanted to erase the one. Okay. Sorry.
But then how do you get rid of this one when you multiply them, the matrices?
I divide them. I take a quotient of these two matrices.
Okay.
Okay. Okay. Any other questions? So again, the proof I know, well, the proof that I read, the first proof that I read, this is in Dave Morris' survey, actually shows more. It shows that the width of the, instead of taking elementary matrices, you take elementary matrices whose off-diagonal term is divisible by n, then the width of this set is also finite and actually is independent of n. Okay, these are not generators in general, but whatever they generate quickly. Okay, and as a corollary, the same proof will show that the width of the conjugacy class of E12 to the n is finite, and actually that it's independent of n. Okay, so as I said, the basic thesis, the basic proposal of this talk is that the notion of finite conjugacy width, so finite width of conjugacy classes, can be used as a replacement for bounded generation. Okay, in the case of SLD, it follows, well, it does. I show you an example where it follows some conjugacy classes where it follows from bounded generation. It turns out that the general case also follows from bounded generation. But I want to say this is a weaker form of bounded generation, and it may be just as useful, or for certain applications. Okay, so let me give you a few indications this is a good idea. First of all, as opposed to bounded generation, finite conjugacy width holds for some uniform lattices. Okay. Second is that it has many applications. Okay, so I'll show some applications to the congruent subgroup property and to model theory. There are also applications to stability, but I'm not going to talk about them now. And maybe the most interesting thing, I think, is that that finite conjugacy width is actually very closely related, more than what I'll say in this lecture, it is very closely related to congruent subgroup property. In fact, it's a variant of congruent subgroup property, but not for the group gamma, but rather for some ultra power of gamma. Okay, so as I said, this is a commercial break, so I will leave the serious things, these two, to Chen in his next lecture, and I want to talk about application. Okay, so first of all, Alex talked about the theorem that bounded generation for the profinite completion of gamma implies that gamma. So if the profinite completion has bounded generation, then gamma has the congruent subgroup property. I want to show the same for finite conjugacy width. Okay. Now, one thing that that you should be aware of, bounded generation for a group immediately implies bounded generation for the profinite completion. Okay, but it's not true for finite conjugacy width. Okay, so the notion of finite conjugacy width for gamma is different from the notion of finite conjugacy width for the profinite completion. Okay. Nevertheless, I want to show that.
You know that it's different. You have counterexample, or just it's.
No, it doesn't follow immediately.
Doesn't, but we don't have counterexample.
No, but I'm giving a talk. Probably it's not how to find. So I don't have one at the top of my tongue, at the tip of my tongue. Okay. Any other question?
What exactly is the definition of finite conjugacy?
Sorry, I can't hear you.
What exactly is the definition of finite conjugacy width?
Oh, I'm sorry. I didn't say it. It's finite conjugacy width. I mean that every conjugacy class has finite width.
Thank you.
But not uniform. It's not the same. Not the same.
It's not the same as. But usually we have some control of this width. They're not all bounded, but we have some control over it. So Chen will in the so I will leave this to Chen, but conjecturally right now it doesn't meet this. Okay, in cases we do know, we have some control over the width. Okay, any question? Okay, so let me prove or sketch the proof of this theorem. Let's do the contrapositive. Okay, so let's assume that gamma does not have the congruent subgroup property. I want to use Rapinchuk's lemma from Alex's last talk. Let me remind you, Rapinchuk's lemma says that if gamma does not have the congruent subgroup property, then there is a quotient of the profinite completion of gamma that is an extension of this adelic group, or I don't know, the pro-congruence completion of gamma, and excuse me, an infinite power of a finite simple group. When this is the case, right? If you have any such extension, you have that G of Z hat acts on this infinite product. Now, let's take the simplest case. This finite simple group can be either abelian or non-abelian. It turns out that the non-abelian case is simpler. In the case where F is non-abelian, okay, think about it. If you have an automorphism, what automorphisms can you have of A5 to the N? Okay, you can take an automorphism in each coordinate, and you can permute the coordinates. That's everything you have. So forget about the automorphisms in each coordinate. What you get is that you get an action of G of Z hat on the natural numbers. Okay? Now everything is continuous here, and G of Z hat is compact, so the orbits are finite. Okay, now, and here come the two key points. First of all, these orbits are unbounded. Okay, they are unbounded because this short exact sequence is actually contained in a bigger short exact sequence that looks like this, the same kernel, a larger group, no longer compact, that contains K. And here you'll have the adelic group, G of A, okay? And again, suppose the action had bounded orbits, it would mean that there is a finite index subgroup of G, Z hat, and in particular of GZ, that fixes F to the N, okay? But inside here, you have G of Q. Okay, so G of Q has a subgroup that fixes F to the N. Okay? But G of Q is simple. Okay, so it means that G of Q acts trivially on F of N, but G of Z is dense, and therefore the whole action is trivial. Okay, and if the whole action is trivial, it means that this is a central extension, and central extension implies the congruent subgroup property. Okay, so the orbits are bounded. And finally, if you take an element, okay, and it has orbit, you take an index, and it has orbit of size n, and you look at, and you take the element inside f to the infinity, where all the coordinates are 1 except a non-identity coordinate in the ith. So non-identity element in the ith coordinate, then every conjugate of this is still going to have only one non-identity element. But the subgroup they generate will have element that has n different and coordinates that are different from 0. So the width is at least n. Okay, so if the orbit is unbounded, you can take an element. So if the orbits are unbounded, you can take some element that has only one coordinate in one non-zero coordinate, one non-identity coordinate in every orbit, and it will have to have width bigger than every natural number. Okay, so so this would be an element here with infinite width, but then if a quotient has infinite width, then so does the group itself. Okay, any questions?
No, I didn't say it again. What you're claiming now, that the orbit of I is size n. This I understand, but
So I'm saying if the orbit, if you have a coordinate, let's say the first coordinate.
I understand. I understood what is written, but did you say something? You already come to a contradiction or not yet?
I was going to. So I'm saying that if I take gamma prime, not this gamma, okay, gamma prime has has a single non-identity coordinate in each orbit, then the width of gamma prime is infinite. Okay, because it's bigger than n for every n. If I restrict only to the part that
I see. You take a diagonal tree.
I take some, yeah, I take an infinite, yes. I take something with infinite support, but has a singleton support in every orbit. Okay, so now I want to make a hard break and talk about different application of, sorry, there is a question in the chat. Oh, so there is a question, why is there an action on the kernel?
When f is non-commutative, why do you get an action of g z hat on the kernel?
Oh, this is a central extension. Oh, sorry, not. You're right. It's not an action of GZ. It's an action of K.
Okay, thank you.
It's an action of K, but so thank you. The same proof works. Okay, and I'm going to talk about the application to the model theory of groups. Okay, so you all know this, but let's just be precise. When I say first order logic or first order language, I mean all the expressions that you can write using quantifiers, variables, logical connectors, parentheses, of course, equality and a symbol for group multiplication. Okay, they should be grammatically correct. So for example, every parenthesis should be closed somewhere. Okay, and but I don't care if it's true or false. Okay, for example, this is a grammatically correct expression. Okay, and that's another grammatically correct, very similar grammatically correct expression. Now there's a difference between these two. In the first, every variable is quantified over. Okay, so when you have such an expression and you have a group, you can say, the only thing you can say whether it's true or false. Okay, and I'll call such a thing sentences. In the second case, not all the variables are quantified over. X is not quantified over. Okay, so if you have a group, you cannot say whether it's true or false, but you can ask. But what you get a set. You get the set of all x's for which this expression is true in G. Okay, so such an expression doesn't give you truth value, it gives you a set. And such sets are called definable sets. Okay, and one of the main questions in model theory is, in first order logic, is how expressive is this language? Okay, and maybe I'll divide it into two, okay, according to the type of sentences. Okay, so maybe I'll write, this is a sentence, this is a definable group, definable set. Okay, so if you want to concentrate on sentences, the question is, how well can you separate different groups? Okay, so for example, 1 is a sentence that holds true if and only if G is a billion. So the property of being a billion can be expressed using first order logic. Okay? And you may ask about different other classes of groups. Are they first order? for the second one, you have many, maybe definable subsets of your model, and you might ask, how big is this collection of definable sets? Okay, so for example, again, example 2 would be defines the center of the group. So the center of the group is expressible as in first order language. And you may ask about different subsets. How they defined? Okay. Now, maybe contrary, maybe contrary to your immediate reaction, usually less expressive is better. Okay, less expressive, especially in the second meaning of the word, means that the definable sets are very structured. So it means that you can say something about them. Okay, usually applications of model theory go like this. I have an interesting set, mathematical set. I know it is definable, and because I know that there are very few definable sets, and it usually means that they are very structured, it gives me something about the set. Mm-hmm. Okay, so I want to, yes.
Nir, I just noticed, I cannot see it, but there is in the chat, somebody wanted to ask or say something. Do you have an access to the chat?
Yes.
No, I asked it and Nir answered it, sorry.
I will open it.
No, just maybe somebody
I'll
wanted
see.
to
Yeah, and nobody, Alon asked a question and
Oh.
okay. So I want to talk about few about our results. This, I think, it's a very striking dichotomy between rank 1 groups and higher rank groups. That and I'll divide it into, I'll call rank 1 flexible, and I'll call high rank rigid. But this is slightly different notions from the usual rigidity, the group theoretic rigidity notions. So let me describe what happens first in the rank 1 case. So this is work of Sela, and it is stated for gamma, which is hyperbolic and torsion free. Okay, so these are not all rank 1 groups, but I think that people believe that something like this should hold for all rank 1 groups. Okay, so first of all, in the sense of definable sets, this is very much non-expressive language. Okay, the claim is that gamma has very few definable subsets, but they're very structured. Okay, the logical notion is called stable, but that I don't want to define. But let me just give you a consequence, such a thing. For example, if you are able to define logically, first order, logically define a subgroup, then it's either the trivial group, the whole group, or it is cyclic. Okay, so for example, gamma may have lots of index 2 subgroups, but none of them is definable. Okay. And on the expressiveness as a, using properties of groups, how well can you separate different groups? This is also very cool. For example, gamma and gamma free product, the cyclic group, are indistinguishable as first order logic. Every sentence that is true for gamma is also true for gamma star C. Okay. Now, the higher rank,
What is called elementary equivalent in the class?
this is called elementary equivalent, yes. Now, on the other side, something completely opposite happens. Okay, first of all, gamma has lots and lots and lots of definable sets. Okay, they are very much non-structured. Okay, so if we're talking about subgroups, for example, but it's much more than that. Every finitely generated subgroup of gamma is definable, but it's more than that. Every subgroup that you can think of will be definable. Okay. And so the language is very expressive, and for higher rank lattice, and moreover, the language can pinpoint the group.
I guess you believe it for all that high rank lattices, but in what generality you can prove it?
Okay, hold on. I will say that. I'll say that in a minute. I'll say that in a minute. And as opposed to this elementary equivalence, gamma here is axiomatizable. Okay, it means that there is a single first order sentence such that gamma is the only group that satisfies it. But again, this is not quite true. I need to restrict to finitely generated groups. Otherwise, it's just false for general model theoretic arguments. You can also always take ultra product or something like this, which would give you a non-isomorphic group that will satisfy exactly the same properties. Okay, but among finitely generated groups, you can pinpoint your group gamma, SL3Z. There is a single first order formula that that will hold true only at SL3Z. Okay, so let me just attribute, this is Tzlil Sela work. This is joint work with Chen Meiri. And part of it with Alex Lubotsky. And the generality in which it is known now is gamma here is high rank. And either non-uniform okay, so gamma contains a unipotent element, or we also know it for some uniform lattices. Okay, so I write it of spin type. So it means it's a lattice inside a spin group, but it can be a uniform lattice of a high enough degree bigger than, I don't remember, 20. Okay, so you need more than 20 variables in your in your quadratic form. Okay? This is not so serious. Okay, any question? Okay, so I want to talk about the main idea of the proof of such a thing, and it's a notion, and it boils down to a notion. It's a logical notion called by interpretation, and it's a fabulous notion. I mean, I'm very happy that it exists. It's actually quite amazing notion. Logic model theory deals with more or less all mathematics. So, and it does it by using different languages. So there is language to talk about groups. There is a language to talk about rings. There is a language to talk about differential equations. there's a language to talk about, I don't know, graphs, combinatorial graphs. And but nevertheless, there are ways to compare different structure in different languages. Okay, so by interpretation is an example of such a thing. So think about it for a minute. If you don't know this notion, how would you give any meaningful relation between, let's say, a differential equation on one side and a graph? Okay, in what way can you say that this differential equation is equivalent in some sense to this combinatorial graph, but the other differential equation is not equivalent to such a thing? Okay, by interpretation is an example of such a thing. Okay, and let me just say it's a kind of Morita equivalence. If you know Morita equivalence from algebras, this is a kind of Morita equivalence. Okay, let me give you the definition, or kind of give you a definition of by interpretation. First of all, I claim that if you take a structure in a language, so let's be more specific, gamma, okay, and the language is the language of groups, then the collection of all definable sets form a category. Okay, what do I mean? I mean that not only do I have the notion of definable set, but I also have a notion of definable map between definable sets. And that's an easy notion. So if I have X and Y definable sets, then I'll say that the map between them, a function, is definable if its graph, so the graph of F sits inside X times Y, and I want its graph to be definable. Okay, so I have a category of definable sets. Okay, the simple definition of by interpretation is that two structures, so a group and a ring, or a group and a differential equation in different languages, are by interpretable if these two categories are equivalent. Okay, now there is an asterisk here because I should add some decorations. So there is a notion of product in definable sets. If you have two definable sets, then the Cartesian product is a definable set, and I want this, and I want these functors that give you the equivalence to preserve product, and slightly more, but more or less this is the definition. Okay, now this is an abstract notion, but let me just say one thing. What does a functor? Okay, an equivalence of categories is given by two functors and the natural transformation. But what does a functor mean? Okay, what does it mean that I have a functor from the definable sets in X to definable sets in Y? Okay, it means that I have a copy of everything that I can say about X inside Y. I can emulate every definable set in X as a definable set in Y. Okay, and this is how information gets passed. Okay, if I know something, if I know that X has lots and lots of definable sets, okay, I immediately get that Y has lots and lots of definable sets. Okay, if I know that yeah, so that's the kind of information that passes between different notions. Okay, so here's the real theorem, and it is that if gamma is high rank, that's either isotropic. So isotropic, I'm sorry, means Now, if you think about it as a lattice, it means that it is a non-uniform lattice, or can be uniform, but of spin type. Then gamma with the language of groups is bi-interpretable with the ring of integers, with the language of rings. Okay, and once you have this bi-interpretation, you have the entire arsenal of Gödel. Gödel's work on Gödel and Tarski's work say that there are lots and lots and lots of definable sets in the integers. We know them very well, so you can pass information to gamma. Okay. Any question?
Yeah, there's something which I must say that kind of confuses me all the time philosophically, because on one end, we are saying that all these lattices are bi-interpretable with Z, so they are kind of similar to each other. On the other hand, they are very distinguished from each other because they have like what we like to call first order rigidity, namely the first order language completely determine the group. So in what sense they are, so what is the meaning that they are interpretable to each other? Not to Z, okay, to Z I can accept, but somehow.
It means that this notion of bi-interpretable is not very discriminating. It means that you can have lots of totally different and think about Morita equivalence, right? You can have a commutative ring, Morita equivalent to a non-commutative ring. Okay, but clearly they are not isomorphic. Clearly they satisfy a very simple property. There is a very simple property that distinguishes them, but still they are Morita equivalent.
Can I say something here?
Yes.
Yeah, I would say it tells you something about the wealth of definable sets in each of those groups. If you use this bi-interpretability by going via the integers, then you'll see that if you have two completely different groups, nevertheless, there's you can find a definable set in one which looks like the other one. So the groups themselves are different, but there's a definable set there which looks like the other group.
Yes. Sorry, I can't hear. I'm sorry.
What is the
Can someone repeat the question?
What is the functor in your theorem?
What is?
What is the functor in your theorem?
Oh, okay. So I want to.
What is the functor?
So this is exactly what I want to explain. I want to explain the functors. I will not explain. That's the easy part. I will not explain the natural transformation. The fact that so an equivalence of categories consists of two functors and two natural transformations. Right? The natural transformations are the hard part, and I told you it's a commercial break, so I'll do the easy part. Okay, so let me explain it in a simple case. Okay, again, what I want is to construct a copy of the integers as a ring inside the group SL3Z. Okay, so again, it consists of finding a set, a function, definable function that emulates addition, and a definable function that emulates multiplication. Okay, so the set is I'm going to take E13, and I'm going to take the center of the centralizer. Okay, it turns out that the center of the centralizers of E13 consists only of powers of E13. Okay, that's a computation that you do. Okay, so first of all, this is my set. This is a copy of Z, right? And moreover, if I want to emulate addition in Z, so I want to take E13 to the A and E13 to the B and map it to E13 to the A plus B, so without parentheses, this is clearly a definable set. It's given by the multiplication, the group multiplication. Okay, so it's very easy to emulate the additive group Z. Okay, but it's not entirely trivial how to emulate multiplication. Okay, I need to now take a different function. It takes me E12 to the A and E13 to the A and E13 to the B to E13 to the A times B. Okay, the way to do this is as follows. You take E13 to the A and E13 to the B, you first conjugate them, okay, to different elementary matrices. So E12 to the A, which is conjugate to E13 to the A, and E23 to the B. And then you take their commutator. The commutator term is E13 to the AB. Okay, so this is the beginning of one functor. Okay, so I need to construct a functor from definable sets over Z to definable sets in SL3Z. Okay, and I just told you where do I send Z. Okay, so I send it to this definable set. Okay, but now once I have Z, and I told you how to emulate the graph of addition and the graph of multiplication, and from this you can you can extend this map to all definable sets. Okay, so I don't know who asked the question about the functor, but did I answer the question at least for SL3Z?
Yeah, so is part of the content here that every definable subset of SL3Z is isomorphic to a subset of this copy of Z?
Yes, yes. But more than this, every definable subset in Z to the 100 is isomorphic. You know, there is, I construct not just a functor, it's not just a map, I constructed a set theoretic bijection between the definable subset in Z to the 100 to a definable subset in SL3Z to the 100. Is this okay?
Yeah.
Okay. Where was I? Okay, so let me just say what else needs to be done. Okay, so first of all, we constructed a functor from, we were able to embed the world of Z inside the world of SL3Z. Okay, the other direction is clear. SL3Z is given as a definable set in over Z. Okay, but we're not done yet. Okay, in order to prove by interpretation, you need to show something about the compositions of these two functors. Okay, so you emulate Z inside SL3Z, and inside it you emulate Z again. So yes, so let me tell you what needs to be proven. Okay, at the end it goes down to the following question. You have this. So let me tell you the composition of the functors. Okay, so you take matrix like this and map it to a 3x3 matrix whose elements are 3x3 matrices. Okay. So this is in gamma. Okay, and this is in gamma to the 9. Okay, and you want to show that this map is definable. Okay, so maybe it will all follow from the following fact. Okay, let me simplify your life. What you need to prove is that the map from gamma to gamma, taking this matrix is definable. Okay, and that's a non-trivial thing to do. Okay, the easiest way to do this is to use boundary generation, but I'm not going to talk about this. Okay, so I'm not saying, I'm saying where the difficulty here, okay, not how to solve it. Okay. Okay, so maybe to finish maybe the last part of this talk, I want to talk about how would you do this without unipotence. Okay, so in SO3Z we could use this trick of center of centralizer to get to a cyclic group, so at least to get a copy of Z, an addition. And in general, you cannot do this. Okay, if your group is not, for example, if your group is not, if you are dealing with uniform lattices. So what we do instead is something, we do it slower, okay? The first thing that we are doing, so let me just say, this is a wonderful trick of Julia Robinson that I want to show you. So the first thing that we do is we show that the congruent subgroups are definable. Okay, and one way to do this is to use width. Okay, let me show you how it's done. If conjugacy classes have finite width, it means that the group, the normal group generated by an element, is definable. Okay, because the set of all conjugates of gamma is definable. Okay, and therefore the set of products of two conjugates of gamma is definable, and therefore the set of products of 100 conjugates of gamma is definable set. Okay, you can write it as there exists x1 up to x100 such that your element is x1 gamma x1 inverse times x2 gamma x2 inverse and so on. Okay, and if you know that eventually this becomes the group generated by the conjugacy class, then you know it's definable. Okay, but now this is normal subgroup, and if you know the congruent subgroup property, then it is almost a principal congruent subgroup. Okay, it is contained in a principal congruent subgroup, and the index is bounded. So if you want to get to the principal congruent subgroup, you can just, add at most 7 elements, and do. Okay.
What do you mean it's contained in a principle? It contains a principle.
What?
You wanted to say that you're using the congruent subgroup property or not?
Yes, but this is a minimal normal subgroup, right? It's generated by.
No, but the statement is you said that this is a normal subgroup, so it's contained in a principal.
So I can choose gamma so that it will be contained in a congruent subgroup.
Sorry, say it again.
I choose a congruent subgroup, and I choose an element.
Oh. Okay, so you are not okay. So you really mean it is contained. You're not using the congruent subgroup. Okay, I thought that you.
No, I'm not using. No, I'm using the fact that it's going to be big in a congruent subgroup.
And why the index is bounded?
So how do I do this?
Bounded in what term?
Okay, so I lied. What I actually do is the following. If I have a congruent subgroup, so I want to hit a congruent subgroup, okay? First, I choose an element gamma inside it, okay? And I look at the normal, I choose an element and I look at the normal subgroup generated by this element. This would be so why do I need this?
Even to know that it's finite index, then if you're not using the congruent subproperty, or you're using Margulis or something like that.
I'm trying not to use okay. Maybe I'll suppose that the congruent subgroup property holds, the strong congruent subgroup property holds. Okay, it's on the notes. Okay, I want to show that a given congruent subgroup is definable. Okay, so I take an element there, and it generates a deeper congruent subgroup. Okay. Right? Because it'll generate a normal subgroup, and normal subgroup has to be a principal congruent subgroup. Okay. Now I claim that the now it may be very deep congruent subgroup, but I claim that I can but the quotient is going to be a finite group, and this finite group is going to be boundedly generated, or have I will be able to generate it using okay. I'm using a sort of bounded generation, so finite width, but for the finite set. I'm saying that if I have two congruent subgroup, so suppose I want to emulate gamma m. I want to define gamma m, congruent subgroup. I take an element here and look at the normal subgroup it generates. Okay, this is going to be another congruence, principal congruent subgroup, gamma n. Okay, it might be very deep.
It's contained.
Yes, but now I claim that the group gamma modulo gamma n has bounded conjugacy width. Okay, and I claim that the subgroup gamma m modulo gamma n is generated by a single element, normally generated by a single element. Okay, and this claim is really a p-adic claim. Okay, the claim is that inside, let's say, G of ZP, if you look at the nth congruent subgroup, it will be generated by a single element, and moreover, it'll be generated fast by a single element. Okay, so my group is actually going to be look like this, the product of gamma and delta. This is going to be gamma m, and both of these are definable because of finite width.
Yeah, okay, no, that's, yeah, if you use the common self property, then everything.
Okay, so now, so again, I can do it in the examples that I said. I can do it and get that all the congruent subgroups are not only defined, but are defined using formulas with bounded length. Okay. So this is where I use some control over the width of conjugacy class. It's not enough to say that each conjugacy class has finite width. I need to know that I can generate congruent subgroups using conjugacy classes of bounded width. Okay.
But you said formulas, then formulas you can just, the argument that you showed says that you don't really need the uniformity on the conjugacy classes, because after you take the first conjugacy class, the rest, you can kind of use bounded generation of the finite completion.
Right, but I need the first to be bounded.
What?
But I need the first one to be bounded. That's exactly.
You need the first one.
I want the width first conjugacy class.
Yeah, you need to be bounded. Yeah, I'm sure. Yes, you are. Yes.
Yes.
Okay.
Okay, the next thing that I'm going to do is that I'm going to find a torus. Okay, I'm going to find a smaller subset. I'm going to define a torus, and I'm going to show that every finite subset of this torus is defined. Okay, now this is a little bit number theory, so I'll go over it fast. First of all, I can talk about if I have an element gamma, and I'm looking at all congruent subgroups which contain it, this is going to be a finite set. Okay, so I can use this to, so I don't have a set of prime ideals, but I can quantify over congruent subgroups. Okay. So now I choose a torus, I choose a regular semisimple element, and I'm looking at its centralizer. This is actually, I can think about these elements as elements in some field. Okay, the field generated by this element, centralizer sits there. Okay, and now I use some property, a number theoretic property. Let me just say this: if I have any finite set of ideals, and I'm looking on all elements in this torus, that for every one of my congruent subgroups, except in this cofinite set, both theta and theta times delta are not in the congruent subgroup property, then this is a finite set. Okay, that's something about rings of integers. And this will allow me to play, by modifying my I, will allow me to get lots and lots of finite subsets. So this is subset of theta, and it is finite. And by playing with I just don't have the time. It's not so important. I am able to get lots and lots of finite subsets of my torus. Okay, and now come the punchline. I want to give you this. The punchline is this: once I know to define lots of finite sets, I can define the cyclic group generated by delta. Okay, let me just say why. I can so an element theta is inside the group generated, cyclic group generated by delta, if and only if there is a finite set X that contains one. Okay, and if an element is there, then G times delta is there, except when G is theta. So for example, if theta belongs to delta, you can take X. You have to take X to be the set 1. Oh, you don't have, but X can be the set 1, delta squared, up to delta to the n. Okay, if theta is equal to delta to the n, you can take this set. Okay, but if theta is not in delta, so your set must contain 1, and then it must contain delta, because because theta is not delta, then it must contain delta squared, and then it must contain delta cubed, and so on. It will not stop. Okay, this will be infinite. Okay, so it turns out that so the upshot is that the cyclic group of delta is definable. Okay, and this is half the work. This is going to be the set Z with the addition. The addition is again going to be multiplication, but then you need to group multiplication, but then you need to prove, you need to construct multiplication. But I'm over my time, so thank you very much.
Can you explain maybe by an example the last argument?
Mm-hmm.
And
This?
That's when it's the way you prove that this delta, the subgroup generated by delta is definable.
Mm-hmm.
Maybe with a concrete example of a delta, I'll give you delta, some matrix,
Mm-hmm.
the 3x3 matrices. What type of what is the X that you are getting here? Just the power. So that's what you showed. Just the power.
Yes. So suppose let's go over here. So again, suppose I know that every finite subset, not only every finite subset is definable, but I can define them uniformly, okay? So I can quantify over finite subset.
Mm-hmm.
Okay, so I claim that G is inside the cyclic group generated by H, if and only if there exists finite set X inside theta, such that it satisfies two properties.
Yeah, that's I remember. But I see. But after the X is just kind of easy interpretation. Now, so for this you are using the congruence property, like because you were using the fact before, right, that the finite subsets are all defined.
How do I prove that finite subsets are definable?
Definable in a uniform way.
In a uniform way. So
Indeed,
Okay, so the proof that I gave here, so everything depends. In order to prove that finite subsets are uniformly definable using a formula of fixed length, I needed the first step, saying that congruent subgroups are definable.
Yeah.
Using a formula of fixed length. Now the proof that I gave, I did use the congruent subgroup property, and I did use finite conjugacy width. We have a different proof that doesn't state this immediately, but it does use the idea of the proof. It does use substantial part of the proof of the congruent subgroup property. So I don't know if it's completely
Some of the
independent.
methods. Are there any questions? First of all, from home, some of the people, please speak, because the people at home with the Zoom, just unmute yourself and talk if you want to talk. Any more questions?
I know you said you won't talk about it, but just in a few words. So the application of width to stability is for uniform stability, like replacing, as you said, bounded generation.
What do you mean uniform stability?
We
don't
maybe
know.
you could.
So you mean uniform stability for all groups of a certain kind?
I'm just, maybe in a few words you can say what is the application as you would describe it for.
So the claim is that for some groups, for example, for these uniform lattices in spin groups, if you have a homomorphism, if you have a map from this group to unitary group, to symmetric group, that such that the product of every two elements is close, the image of the product of two elements is close to the composition of the images of these elements, then there is a nearby homomorphism.
Okay, I see. Thank you.
But it's for a fixed group. Now, we would like to know, because right now our width results are not uniform in the group. Okay, we can prove width for very specific groups, but
can you say something?
Nir, at some point in this seminar, I believe that we will get to this uniform stability.
Right.
Maybe then I'll make sure that somebody also will describe the connection with bounded generation or with this width. Yeah, I mean, it's not for the time after 1250. We cannot promise to try to finish on time.
Yeah, great. No, I just wanted to make sure it is that.
So thank you, all of you. Next week we'll have Chen Meiri, who will, I guess, will take us back to the group theory and less than the logic, right? If I remember correctly. And in 2 weeks we'll get Andre Rakinshu. We'll talk also on some bounded properties of arithmetic groups. Some will stay in the same atmosphere, but the talks will be somewhat different. Okay, thank you very much, Nir.
Thank you. Thank you all for coming.
For all of you.
Thank you. Bye-bye.
Bye-bye. Thank you. So that we'll talk today. So the question is, my main question is this, I wanted to get a feeling of what you are interested or what did you study, because some of you said what kind of, so remind me, what are you now? You are third year? And you want to read kind of above the standard material. What did you like in what we talked?